I had to confess that when Ricardo and Raul asked me to give a lecture for this school, I was a bit hesitant. Um, my current area of interest is optical follow-up of gravitational waves, and uh, and I'm interested in understanding the equation of the state of neutron stars and rapid nuclear processes and how all that informed the light curves that are expected to get from observing these events. But that was too much for me. I know very little about it. It was going to be tremendous amount of work, particularly after 1 week of work trying to think hard about how to do multi-messenger astronomy here in America. And so I decided to go on the light side of gravity. And after being 30 years in the field, I had a chance to read a little bit about the history of gravitational wave detection. I thought it could be interesting, and they say yes because they're kind people. So here I am. Uh, there's many references about the subject, and Satellite's Law is a magnificent one. It's a work by Abraham Pace that is extremely informed. It's a technical book, but very historical, and particularly reading about the um, how Einstein was the genesis of Einstein thought is a really very very good book. There are a few other books here, and there is a much more current edition of Harry Collins, updated up to. We didn't write a book about the history of gravitational waves, but we uh, wrote a little bit about the history of gravitational waves in our book. So I'm doing a little bit of publicity. It just came out a couple of months ago. And so the prehistory of gravitational waves. So the first one to ever mention or put forward the concept of geometry be fundamental for gravity was William Clifford, the same one from the Clifford algebras. If you somehow be related to theoretical high energy physics, you probably heard the name. And so he said that small portions of space are in fact of a nature analogous to little hills on a surface which is on average flat, namely ordinary laws of geometry, so like Euclidean geometry, are no value for them. That the property of being curved or distorted is continually being passed on from one portion of space to another after the manner of a wave. So I found it quite interesting when I learned that he said that in the mid 19th century. By the way, in the 1870s, he was on an expedition to observe a total solar eclipse in Italy, and he was involved. He survived a shipwreck in the coast of Sicily. And Laplace thought for what would happen if gravity propagated at finding speed, and he had a very, very particular motivation. He was trying to explain the motion of the moon. What is interesting here is you think, well, the Earth is telling the moon, finding amount of time how to move, and the moon is taking some time in register that and getting back to the Earth, and so on and so forth. This is actually what modern times is called back reaction, which is a current area of active study in general relativity. And but his calculation failed to explain the secular motion of the moon, which was quite a bit of a complicated problem. It was related to the fact that the moon wasn't solid at a certain time in its history. And 1900s, Lorentz conjectured that gravitation can be attributed to actions we cannot propagate faster than light. And then, for the first time, Poincaré used a term that is pretty much gravitational wave like we know it today. And So everything started with the weak field approximation that Einstein took just 1 year after developing the Einstein's equations. And so that was simple, take the Minkowski metric and think about a very small perturbation, and you crank the machine, and eventually you get out the wave equation. And then took another couple of years and to figure out what could be the source of such radiation, and he developed the quadruple formula that actually needed some correction because some factors wrong first, but it was clear that there was a formalism very similar to electromagnetic radiation. And so although there was an approximation, it provided a mathematical framework to do gravitational waves and study gravitational waves, but there were no astrophysical sources. And so very few people thought that gravitational waves could be real. So there was, I should say, probably more than some skepticism regarding the detectability of gravitational radiation. So there were no known solutions of Einstein's equations representing astrophysical objects emitting gravitational waves. Well, we still don't have them because Einstein's equation is extremely complicated. So 10 set of very nonlinear equations where the variables for which are the metric are very coupled. And what was interesting is that just barely 20 years after developing the theory of gravitational radiation, Einstein, in a letter to Max Born, he said, and I'm reading, this is in the letter, together with a young collaborator, I arrived at the interesting result that gravitational waves do not exist, though they have been assumed as certainty to the first approximation. This shows that the nonlinear general relativistic field equation can tell us more, or rather limit us more than we have believed up to now. The collaborator was Nathan Rosen. And interesting enough, just 1 year after the letter to Born, he published this paper with his collaborator, it was just essentially presenting in the linear approximation cylindrical waves. So it's a solution that represented cylindrical waves. And so what happened in that year between 1936 and 1937? Well, as far as I understand, we only learned what happened in 2005, when the Physical Review opened their logs, and it was clear that the paper presented by Einstein and Rosen in 1936 was reviewed by Percy Robertson, the same one of Robertson, Freeman Robertson Walker, and who was actually an expert in general relativity. And so he found that there were inconsistencies. So there were mathematical errors in Einstein's and Rosen solution. So he returned the paper with comments. Einstein got outraged because how dare someone find something about his paper? Furthermore, how dare the editor send it to someone else to be read? Because in the German journals, it wasn't customary to have referees reviewing papers. This is actually a custom that started in the United States and pretty much about that time. And so he withdrew the paper, and eventually, what is interesting is that there was a lot of conversation with Robertson, and Robertson, without never revealing his identity, told him exactly what was wrong. Einstein learned what was wrong, and then he submitted the paper for publication in its correct form. And what is much less known is that actually that solution had been already found 11 years prior by Guido Beck. Guido Beck was an Austrian physicist who had a very interesting life because he was a student at Hans Thering in Austria, and then he moved to Odessa to help building Soviet physics, and then eventually back to Europe, and of course was persecuted because he was a Jew, and he emigrated to Argentina, 1943, and in 1944, he founded the Argentine Physics Association, which was the first one in Latin America. 1951, he moved to Brazil, and he worked at the Centro Brasileiro de Pesquisas Físicas and actually at the University of Sao Paulo as well. And so he was extremely influential in developing physics in Argentina and in Brazil. And so continue with this history. There was a problem of the motion of a wave source. Einstein, Infield, and Hoffman developed in 1938 the method, which actually was the first trial at developing the post-Newtonian approximation, and it was obviously it was clear that the motion of particles gets completely determined by the field equation, which is not something that happens in electromagnetism, where you have Maxwell equations and then you have to add on the Lorentz force. So in that sense, they're completely self-contained. And but the one big problem is that the two-body problem does not have an analytical solution that you have in Newtonian gravity. So, of course, then the solution of considering Newtonian bodies that are moving slow, and you can do an expansion in powers of V over the speed of light, and in the potential, and this is the post-Newtonian expansion. But as it was applied, it was difficult to do that, particularly to keep going order by order, and people were getting mistakes in calculating the quadrupole formula using this, and so there was a time of a lot of doubt about the true existence of gravitational radiation. In 1955, it was precisely the year that Einstein passed away. And there was a conference that was organized. Pauli was the chairman of the conference, and it was honoring the 50th anniversary of special relativity. But it was the first gathering of people working in general relativity. And so the things were the structure of the Einstein field equations, the initial value problem. Ivan Shukewura was at that meeting and started showing how the problem could be solved, and that was quite important in terms of understanding the Cauchy problem, initial values, and how you can get a well-posed theory of gravitational radiation. And but there was not much attention to gravitational waves. Nathan Rosen was participating in the conference, and he basically reviewed the work he did with Einstein, and continue expressing doubts about the existence of gravitational waves in the full nonlinear theory. So whatever they were getting, it was considered to be non-relevant because it was in a linear approximation. And he also said that the plane wave solutions of the linear theory do not correspond to any exact solution of the full theory. And there was another conference, and this one is started to be called GR1, and this conference took place in 1957. This is a very interesting conference, and eventually in 1971, the International Society of General Relativity and Gravitation was formed, and then they counted back and they assigned the number one to the first conference, and from there on, all the international conference of the society that happen every 3 years are numbered in a sequence. So Feynman attended the conference, and Richard Feynman, and he said, that the biggest problem that the area of the in general, he was talking actually in general about general relativity, is that there were no experiments, which was true. By the way, in the previous conference, there was just only one presentation about experimental um, uh, research in general relativity. It was an update on some measurements of the gravitational redshift for some star, and some updates regarding the measurement of the deflection of light during solar eclipses. But actually, they weren't really great advances in experimental relativity that were presented. So he said that how to deal with problems where no experiments are available. Well, you can try a mathematical rigor or play games. So the attempt at mathematically rigorous solutions without guiding experiments is exactly the reason the subject is difficult but not equations. And he presented one of the first thought experiments showing that gravitational waves should carry energy. That was one of the things that was in doubt at the time. So essentially, he said, pick up two particles that, of course, they're going to move when you have a transversal wave. And what's going to happen is put the stick to one of the particles, and in such a way that with the gravitational wave, as it moves back and forth, touch the other particles, there's going to be friction generated, and you're going to measure the heat. And also, Bondi presented another thought experiment at that conference. But essentially, just a few years later, at another conference on general relativity, it took place in Warsaw in 1962, Feynman was extremely skeptical of any progress in the field. And he said, I'm not getting anything out of the meeting. I'm learning nothing because there are no experiments. This field is an active one, so few of the best men are doing work on it. The result is that there are a host of dopes here, 126, and it is not good for my blood pressure. Remind me not to come to any more gravity conference. This is actually in the letter to his wife. And so let's do a recap. This was early 60s. So in 1936, Einstein and Rosen published their cylindrical waves equation. In 1938, Einstein, Infeld, Holtzman, and the first Newtonian order. One of the things that is interesting, at least there's no, at least to my knowledge, no clear explanation, or no record at least, is that Einstein had ever attempted at just look at two stars, binary system, and calculate the power or the strength of the gravitational waves. He mentioned in writing that they were extremely weak. So it's most likely that some calculation was attempted. But I believe that the first record of a calculation using the quadrupolar formula for a binary system was done by Lambda and Lifshitz in their famous book about field theory that was published in 1941. Freeman Dyson, I think, also did that calculation, but for totally complete different reason, and probably I think it was a bit afterwards. And in the 1955, Rosen argues that a gravitational wave cannot carry energy. 57, it was when Bondi and Feynman, that just showed his thought experiment, showed that gravitational waves can carry energy. And 62, Bondi developed this formalism. One of the biggest problems in general relativity is that energy is not local, which means it makes it very hard to talk about what is the energy of a gravitational wave in principle. And in this formalism, Bondi developed something called the News function that was calculating things in infinity. So there was a powerful mathematical formalism, and was showing the system that they were emitting gravitational waves were losing mass. It should be expected. And in the 60s, there was the first book that talks about gravitational waves. It's a book by Einfeld and Plebanski. And but look at the incoherence. In 1965, Smith and Havas, using fast motion calculation, find energy being gained by binary systems. Chandrasekhar and Esposito do the calculation right, and they recovered the correct quadrupole formula for binary star system. And but still in '79, Rosen was arguing that binary stars do not lose energy. So this this time in the history of general relativity is quite interesting because it was highly mathematical, but eventually it was quite a bit of funding going into general relativity in spite of being quite mathematical. So this part of the history of general relativity, I think, is quite interesting. Roger Babson, he created a foundation called it Gravity Foundation, and he was MIT alumni, and he thought that there was a way to prove the existence of anti-gravity. What is interesting, he had friends in the military that also got enticed to do research trying to prove the existence of anti-gravity. So this photograph is from a frame in a movie that is called The Man Who Stared at Goats, which is based on a book written by John Ronson. And what is interesting about this book, by the way, the book is not a comedy. The movie the film is a comedy. It's a dark comedy. But John Ronson was arguing against the army in the U.S. and particularly questioning many tactics that they have. This was actually timed with the problems with the prisoners in the Iraq War, the Abu Ghraib, and he was trying to tie the two different times. So that's eventually beyond the scope of this talk. But the truth of the matter is that there were people in the United States, particularly in the Air Force, that were interested in trying new age theories, particularly in psychology. And it was also a time where they were interested in seeing if anti-gravity could be something that could be found. And they were funding gravity at a level higher than the National Science Foundation. What was interesting is that the physicists that they hired were doing the right things. They never tried to find anti-gravity. They did serious good research. Jeff Winiker was there. Joshua Goldberg, that eventually went to Syracuse, where Peter Bergman was, who was a student of Einstein. And Richard Isaacson was also working at the Wright-Patterson Air Force lab, and who was influential, tremendously influential in arguing for the funding and building of the laser interferometer in the United States. Eventually, a Mansfield Amendment in 1969 stopped the funding because this amendment was essentially tying funds to things that were immediately practical to the armed forces, which wasn't the case, obviously, with gravity. And so all this period that goes between 1930s to 1960s, actually the historian of general relativity called John Einstein, and he called it the low watermark. So what is interesting is that Richard Isaacson, because he needs to leave the Air Force, he goes to work at NSF, where a program in gravitation gets funded and started. At the same time, what is happening is that there's a revolution in astrophysics that is changing our understanding of astrophysics. In the 30s, Carl Jansky opened the field of radio astronomy. And one important result during the low water mark, was the development of the Tolman-Oppenheimer-Volkoff equation that was clearly showing what could be expected in terms of stellar evolution. So this is an equation that is similar, that essentially puts a limit on compact stars that are heavier than 1.3 solar mass, which is a limit for stars to become white dwarfs in the Chandrasekhar limit. This is a time where Weber, who took a sabbatical, he was at the University of Maryland, he took a sabbatical at the Institute of Advanced Studies, and I believe it was, if I remember correctly, Wheeler that convinced him to try an experiment to detect gravitational waves. So he started thinking about using resonant bars. And they were very narrow band and limited sensitivity. But I want to dedicate 2 or 3 slides to this because in spite of, he's remembered for claiming falsely that he detected gravitational waves. This is not totally fair that it goes into history that way, because he developed an exquisite experiment at the time with the technology of the time. And I also like to see this and read the abstract because it's quite interesting. Observation of thermal fluctuation of gravitational wave detectors. So this is the first paper in the Physical Review Letters about his bar. And he said, we report operation of apparatus to measure the Fourier transform of the Riemann curvature tensor. So it's interesting how he reports and how he presents this. But it was very serious, and he got these instruments to be sensitive to strains of 10 to the minus 16. We know nowadays that this is 5 orders of magnitude, higher than what was required. But it was a first step, and particularly because it called the attention of a group of experimentalists that thought harder about the different way of detecting gravitational waves. And he had a student called Sinsky, and this is what is interesting is how they were calibrating their bar to be able to know exactly what they were measuring, and he used another bar that and they were moving this bar and detecting the motions on this other bar because of this. So what they were doing essentially is changing the Newtonian gravitational field, but they were able to measure the variations on the actual bar. Eventually, many people tried to replicate. There was a slide where, and sometimes I thought I wasn't going to have the time, where he claimed that he detected gravitational waves. So I should have probably put it there. And so he claimed in the early 70s he detected gravitational waves, and but several experimentalists tried and noticed at the IBM labs that they're working at the time doing fundamental science, and they couldn't detect anything. And Weber still claimed that he detected them. He even detected. He claimed he detected gravitational waves associated to the explosion of supernova 1987A, which is one of the closest ever in the last since Kepler's supernova, I think, the closest to our galaxy. And I was at this meeting. There was in honor of Newman, who was my advisor. I was a postdoc of him at the time. And I remember Weber and Thorne arguing. And particularly the community that was already been under development, look, it's early 90s, that was betting on the support of NSF funding the interferometers, wanted to make it very, very clear that there were inconsistencies in Joe Weber's claim. And this is another claim in particular that was done in consonance with the Weber's bar in Maryland, and another one that was in Rome. In Italy, there was a big group working in bars at the time that eventually many of them moved to Bed-Ligo. And so the interesting point is all this new astrophysics. In 1950s, the quasars were discovered, and so there was a really very quick development of astrophysics at that time. Jocelyn Bell and Anthony Hewish discovered the first pulsar. They dubbed Little Green Man, and because it was very strange at the time. And this was an extremely important discovery. In 1963, Martin Schmidt at Caltech discovered the first quasar, 3C273, which, by the way, this is one of probably the only one, as far as I know, that you can see almost naked eye with an amateur telescope, the optical part of the quasar. And also 1963, the chirometric, and so this is essentially marking the birth of relativistic astrophysics. And of course, in the 70s, the first binary pulsar is discovered, and it was studied for many years. So they went on to win the Nobel Prize in Physics for their study, and that was the very first indirect confirmation of the existence of gravitational waves, and was, of course, tremendously influential in deciding to build the interferometers. And so probably many of you already know the characteristics of it. So the periastron advances 4.2 degrees per day. And so the system is losing energy in the form of gravitational waves. I mean, the only theory that could explain it at the time was general relativity, and it will coalesce in 300 million years. And what is interesting is comparing the 4 degrees per year with Mercury's perihelion precession, that is 43 arcseconds per 100 years. So look at the several orders of magnitude difference. So it was a really, truly relativistic system. In the 70s also occurs the discovery of gamma ray bursts that started, by serendipity, just because they were monitoring compliance with the nuclear testing ban. There was the treaty with the Soviet Union at the time. And of course the GRBs, you already heard a lot about this. We're roughly classifying in two types, shorter than 2 seconds and longer than 2 seconds. And what is interesting is it's only very, very recently that we know that the ones that are shorter than 2 seconds can clearly be identified as the coalescence of binary compact systems. And well, you also saw a slide about this just very recently. X1 was the very first black hole ever discovered, and Stephen Hawking lost his bet. So black holes are real. And in parallel, at that time, there was a push for developing a new type of gravitational wave detectors. So this is the main Soviet physics journal from you can see it's early 60s, and what it's showing is that it is shown that the sensitivity of the electromechanical experiments for detecting gravitational waves by means of piezoelectric piezo crystals is 10 orders of magnitude worse than that estimated by Weber. So he was using this transducer piezo crystals, Weber. In the low frequency range, it should be possible to detect gravitational wave at the shift of the bands in an optical interferometer. And then eventually the paper goes on to explain that the best bet for doing that type of interferometry is laser. And so there was a proposal put forward by Ray Wise and then a consortium, Kip Thorne, got convinced that that was a way of detecting gravitational waves. And so the National Science Foundation decided to seriously consider building the interferometer. What is probably not so well known is the opposition at the time, and particularly the astronomical community was fiercely opposed to it. And they had probably some good reasons. It was going to take a good chunk of what could be the budget for research in astronomy. So this is an article in the New York Times that is showing a poll that Dyson, who is a U.S. physicist, conducted with about 2,000 astronomers, and he said he got 60 replies, and they were 4-1 against LIGO. And Anthony Tyson in particular, he went to a subcommittee of science from the Committee of Science, Space and Technology in the House of Representatives when the construction of LIGO was under consideration. Remember, this was in the order of hundreds of millions of dollars, so it couldn't be just a proposal you submit to NSF and a panel review of peers recommends it gets funded. It had to be approved by the U.S. Congress. Eventually it went to over the $1 billion cost. So as an expert witness, Anthony Tyson said, imagine the distance around the world, 100,000 million times. The total is 3,840 billion kilometers, a million times the distance from Earth to Neptune. Take two small objects separated by that distance. Strong gravitational wave will modify it less than the thickness of a human hair. There is less than a few tenths of a second to measure this, and we don't know if this event will happen next month, next year, in 30 years. And by the way, he didn't say anything that wasn't correct. This is essentially correct. But the project was funded. And eventually, the first stage of the project was, to build a prototype interferometer. There was a 40-meter interferometer that was at the Caltech campus. It's still there. And there was, it's interesting, going into project of this kind requires an entrepreneurial mind. You had to manage it like, in some sense, like a factory. Everything has to be on-time production, otherwise things don't work. And of course, scientists like to do their experiments. So there was, fights between Ron Driver, who always wanted to tickle with experiments, and Bob. I remember in 1992, there was one of the GRs. I don't remember which one was. It was 11. It was in Cordoba, in Argentina. And Ron Driver was at the meeting when he went back to Caltech. The logs of his office had been changed, and he couldn't get in. And it was a big fuss. And so NSF intervened and essentially put in charge someone from outside. That was Bayer Barish, who was actually engaged previously in another big experiment that was superconductor super collider that Reagan killed in the early 90s. And so he had expertise to lead an experiment of this scale. This is a photograph from 1996, and this is in Livingston. This is Gabriela Gonzalez. Some of you might know. She was the spokesperson of the collaboration when the announcement was made of the detection. And so she was a postdoc at MIT at the time, working on the LIGO group. And she was coming to visit me in Brownsville, Texas, where I had just recently took a faculty position, so it's almost 30 years ago, and I was in charge of developing a new program in physics. So he took this picture, and they convinced me that the coolest thing I could do in physics was LIGO. That's when, in 1997, I formed my LIGO group at Brownsville. And eventually the detectors were built, and of course, these guys went to win the Nobel Prize. And it's unfortunate that Ron Driver, that in terms of the interferometer technology, did so much, didn't even get to see all this. And I'm going to say a couple of things about numerical relativity, because this was, I think it's quite important. In the 90s, actually in the 80s, 80s going into the 90s, NSF dedicated a big amount of funding, particularly because of LIGO, to developing a theoretical framework. The idea was try to model the collision of compact objects using Einstein's equation, full Einstein equations that can only be done numerically. It was complicated because there are singularities, so you need to develop a technology to treat these singularities. And also it was computationally intensive. And the project, I think it was called the Grand Challenge Alliance, and eventually it didn't go that far. And there was a particular project called the Lazarus Project that in the late 90s, early 2000s, made some progress, because it was essentially trying to not do full-blown numerical relativity, but using some approximation techniques. And but eventually, a full evolution was achieved for the first time in 2006 by two different groups. One was with us in Brownsville, Manuela Campanella and Carlos Lusto, and the other was NASA, the Goddard Space Flight Center, and they were both published in the same issue of Physical Review Letters. And well, the end of this long journey happened, as this is now something that you all know. In 2016, it actually happened in September of 2015, but it wasn't published and announced until then. And so September 14, both LIGO detectors detect the coincidence signal, and the signal was observed with a match filter signal to noise ratio of 24, so extremely high, and a false alarm rate estimated with less than one event per 200,000 years, which is a significance larger than 5.1 sigma. And the physical parameters were this. And what was important is it was a truly historic result, credibility of the intervals, but the observations demonstrated the existence of binary stellar mass black hole systems. And it's the first direct detection of gravitational waves, and it was the first observation of binary black hole merger. And from there on, then it was a bit easier to go into a multi-messenger astronomy. So probably the first experiment in multi-messenger astronomy is our sun, right? 1968, the first neutrinos detected by Davis. But if you don't want to count this, then you have supernova 1987A, which was photons and neutrinos in 1987. But the only truly, so far, gravitational waves and the full electromagnetic spectrum has been GWA 170817. There are two other ones, this blazar, and sorry, one more that was in neutrinos and in electromagnetic, that was this blazar. And so I myself got incredibly excited, more than probably with the first gravitational wave detection, when this one happened. I'm particularly showing just the one that we got 1 day later about GW, the first kilonova. By the way, this image was taken with a Brazilian telescope in Cerro Tololo. And so there was this bright spot. The galaxy is masked, and this is the kilonova at the second day. And of course, there were much better observations than this. But so two neutron stars. in the galaxy NGC 4993. They collided 140 million years ago. The gravitational and electromagnetic waves traveled from this big explosion, reaching our Earth. And gravitational waves were detected first by advanced LIGO and advanced Virgo. And then gamma ray burst was detected by Fermi and Integral. And then eventually the kilonova was detected by several groups at the same time. So this truly started in a grandiose way, multi-messenger astronomy of gravitational waves. And so this one probably you all saw it, but it's a cool animation. So let me show it as well. And particularly because you can see the range of the electromagnetic spectrum and the days as they're coming up. Of course, radio is going to be the long-standing ones at the very end. And that's a beautiful animation. That's it.
Thanks, Mario. Questions? Comments?
So I have a comment. I have a microphone, so I took the word. So I was, while you were saying there about the prehistory of, let's say, ancient history of gravitational waves, I was thinking exactly about Richard Isaacson. And then when you mentioned that, it was amazing that he wrote in his PhD thesis about exactly the stress energy tensor that it's not really a stress energy tensor, but it's something that works exactly as a stress energy tensor for fluctuations of the gravitational field. And that was 1967, and he published in 68.
Yeah.
And then he became NSF director for that same thing. So in some sense, he himself went to prove that in theory that it had to exist, and he had a key role in advancing the experiments that made a confirmation of that. So it was one of these accidents of history which are really amazing. And if you look at Mr. Thorne-Wheeler's book, there is a page for that result in that book, even though it was a very recent result. Anyway, just a comment.
No, but it's a good one. His role was, and his contribution to the field where, like you just described. So there are many things that happen in these 100 years. This is 100 years. It's a long time. And even worth discussing is all the process that goes from, I believe in 2001, is what you would call the first slide. So when the first scientific run on LIGO, a very, very low sensitivity, but still people taking it very seriously. And then eventually, all the mock challenge of trying to detect an injection. And at the end, when it was actually found by the collaboration, opening champagne, I mean, it's, and also upper limits. There was an upper limit. It was the gamma ray burst, short gamma ray burst that was observed at the time of initial LIGO. And initial LIGO managed to give upper limits and said there's no gravitational wave associated, which means this cannot be binary compact merger. Most likely it's a magnetar, sub-gamma repeater. And so there were some astrophysical results, relevant astrophysical results, even with initial LIGO, non-detected gravitational waves. And